Okay, welcome back. I would like to start today with a short summary of what we have seen yesterday. And I'm sorry, I have to apologize. I went a little bit over time yesterday. I hope I can compensate a bit for that today. And I also hope this doesn't discourage you from asking questions. So I will promise you today I will make it on time so that we can have lunch before past. So what have you seen yesterday? And I'm also writing just this short summary in order to give you another opportunity to ask questions, because yesterday I ended maybe a little bit too late, so you didn't have time to ask all the questions you may have had. So what we have seen is a framework, and for describing thermodynamic systems, and the main ingredients of the framework was that we said there is a set of states, so there's a set that a system can have, states of a thermodynamic system. And maybe I called this sigma just as a reminder. And we said we also have to specify a set of possible, what I called adiabatic, but this was just a word, transformations. And I called that A. And what adiabatic in some way means, you could also think of it like without, that this was without the help of another, was without involving another thermodynamic system. So you could, in some way, if you want, you could take the point of view of, let's say, an experimentalist, and you could go to your lab and say, let's identify a system that we want to treat using the framework of thermodynamics. Then we first have to ask ourselves, what are the possible states of the system? And the states are essentially just the description of the system using parameters that you can determine. For example, let's say the volume of a cylinder or the pressure and so on. So this specifies this set, and then you have to specify also this set. So you have to ask yourselves, what are the transformations that you can carry out on the system without involving another system? So if you just look at the system as an isolated entity. And of course, you have to do that for all the systems. So you have to also do that for composite systems. So if you, for example, want to analyze a machine that is connected to a reservoir, then you should consider the whole thing as a big system. And then you can again ask, what are the adiabatic processes for the big systems, which, if you focus on one system, is of course then no longer an adiabatic process. So what I'm saying is that if you have here a system, and here you have, for example, a reservoir, then of course a process described on this total joint thing, an adiabatic process, so to speak, which means that it doesn't involve an additional extra system, is, if we restrict our attention to this system S, of course, not an adiabatic process. So if you have here a heat exchange, then this is adiabatic for this total thing, but it's not from the point of view of that. So you have just to determine this set A for all the systems and joint systems and so on. And once you have done that, you can start doing your analysis. So this is the only input you need into the mathematical framework. And then what you do is you can now go through the thermodynamic laws, so the first law and the second law. And these laws will tell you whether you have a consistent description. It may be that you find out that the first law tells you that certain processes are missing, that you cannot transform from one state into the other, and then you have to ask yourself whether you missed that or whether there is an inherent impossibility. Or, for example, the second law that forbids certain processes may tell you that you have included a process which would allow you to break the second law. So in that sense, these laws are kind of statements about, let's say, these two sets formally, about this set and this set. And if you break the law, and we will see examples today, you have to ask yourself whether this is now has a physical reason. Maybe you included too much into this set, or there is, whether is, I mean, the other possibility is that indeed you have found a system which actually really breaks the second law, which means that you can then extract work at no cost. This is also always a question you have to ask, but usually the answer is, of course, that you did something wrong in your modeling, and the second law still holds, as we will see today in some of these examples. Let me also briefly remind you of the example we had, because I will continue with a very similar example. So I will just sketch it here. So you remember I considered a gas consisting of two types of particles, and maybe I do it like that. So here's a wall, and we had one type of particle that I indicated with crosses, and another one type of particles that I indicated with little balls. And you could think of, for example, two different isotopes of the same chemical element. And now we could look at the process where we remove the wall, so that after wait a bit, and once we do that, we will find, of course, a mixture. So I indicate that here. Now we have analyzed that from the point of view of an observer who knows about this fact that there are two different types of particles. I called him observer 2015, so this is one who has the technology to distinguish these two types of particles. And this observer can now make statements. For example, he would say that this process, so let's call this process R, removing a wall, R, he would say it's irreversible. That's what he said. And he could actually calculate the entropy change if you go from here to here. So the delta S in this process R, and I will want to do the calculation now. This will actually be one of the exercises, but I already mentioned the number will be nRT ln2. R is the gas constant, N is the number of moles we have in the gas in total, and T is the temperature at which I do this process, or of the gas. So we assume that the temperature stays the same. This is, for example, the case if these are ideal mixtures. So this is the analysis that this observer would do. Now, I also said we could have asked ourselves, how would an observer from 2 centuries ago analyze this process? So what he would see, so we would give him the same system, but he would be unable to see what type of particles we have. So he would have that, and now he would also remove the wall, and of course, in this case, the situation would just look like this. And now, obviously, if I just analyze this situation, then I would say this is the process of removing the wall R, in this case, is reversible. I can introduce it again, and we'll get the same thing again. And actually, I could also calculate the entropy, but it already follows from the reversibility that the entropy change is 0. Okay, so that's what I told you last time. And so there are a few important things to note here. So the first is both descriptions are perfectly fine. So I'm not claiming that one of them was wrong. However, what we are saying here is that the notion of entropy, as it is used here, is actually a notion that connects or that somehow quantifies the information that an observer has about the system. As we will see that when we can analyze the same thing in statistical mechanics, then it's maybe more obvious, rather than being a property of the system itself. So it's clear that when we go from here to here, this observer loses information. And this is just because he had originally more information. Whereas this observer here, he doesn't lose any information when we go from here to here, because he didn't have this additional information that there are different types of particles, that one sort is here and one other type is here. He never had that, even at the beginning. So he cannot lose the information. So in some way, you could say this observer starts with less information. He simply doesn't know this distinction, therefore he doesn't lose it. And this one had additional information and lost it. So that explains the difference of these two things. But of course, both statements are correct. So there's nothing wrong. But what we have to be careful about, and I think the examples we will see today will show that this is really important. I mean, this is likely an artificial example. We will see more natural ones. So what I will also remind you of that later. What we have to care about is never to mix these two things. And sometimes, I mean, here it's kind of obvious that they are different, but sometimes it's not so obvious that we are suddenly jumping from such a description to such a description. That's forbidden, because then we are essentially working under two different notions of what is possible. We would kind of mix the assumptions that we put in here with the assumptions we put in here, because of course this observer would put in a different set of possible states and a different set of possible adiabatic operations, and if we mix two things, then obviously we can get inconclusive or even contradicting results. So that's what we should learn from that. Don't mix these two things, just stay within one thing, then we are fine. This is also important that we are fine, because it would be very strange if this observer here would have done a wrong analysis just because he was missing information, because that's probably always just a fact. Even today, there's no one who tells us that we know everything about the system. Maybe someone detects additional properties in the future as new physics, and we don't want our analysis to be wrong because of that. It's maybe incomplete in the sense that one can make additional statements, but it shouldn't be wrong. So let me just stick a little bit with that and ask ourselves, what conclusions do we draw if we do the same analysis, or we consider the same system but in statistical mechanics? And in that case, we would actually get the same result. So let me remind you that we made this distinction between phenomenological thermodynamics and statistical mechanics, and this calculation that was here was all done now in phenomenological thermodynamics. However, if you do statistical mechanics, we would instead start with a microscopic model, and this model is already suggested by the drawing. We would assume that there are actually these different particles. So maybe I should also remark that everything I said so far didn't rely on the fact that these are really particles. I could have said everything by just saying these are two different substances that we mix. So we never use the particle model. This is an important property of the phenomenological thermodynamical model, that it doesn't rely on a particle model. The only thing I would say differently here from here is that here it's one substance, and here we have two different substances, but that they are consisting of particles was irrelevant. However, if you do now the analysis in statistical mechanics, we use a different notion of entropy that you may, of course, also know. And this notion of entropy depends now on the probability distribution of the underlying particle position. So in statistical mechanics, we assume there are particles and they have a certain probability distribution. And then the entropy can be written as let me write it in the discrete case. Of course, you can replace the integral by the sum by an integral to get the continuous case, but for our considerations, it's more useful to consider the discrete case. So let's assume x are the different states that the system can have, and px is the corresponding probability that the system is in state x. And then the entropy is given by this formula. There are different versions of entropy. If you're an information theorist, you may have seen it without this constant and with ln replaced by a logarithm to the basis 2, but this just differs by a multiplicative constant. So this is the entropy. Now, in the particular case where, so if P is a uniform distribution, then it's easy to see that the entropy is essentially just reducing to kb times the logarithm of the number of different states. So this is equivalent in the case where it's uniform. This is obvious because in that case, if it's uniform, each probability is just 1 over the number of states, and so the 1 over can be compensated with this minus, and you get this thing. So you certainly have seen that. This is usually also kind of called the Boltzmann entropy if one calculates that independently of the probability distribution, but in case it's uniform, the two entropies coincide. Now what would that, now we can compare again the two observers. So we can say, what would the observer, so what are the number of states that the observer 2015 would attribute to the system, and what are the number of states that the observer 2000 or 1865 would attribute? And what we find is that, of course, there is first of all the number of positions and momenta these particles can have is kind of the same in both situations. However, for this observer, each particle can be of two types. So we have an additional factor of 2 to the n, where n would be the number of particles. So in other words, the modern observer has just a larger state space, and the state space is larger by this factor. And I don't even need to care about the number of states that this has. I just know that the one is larger by this amount. So if I now insert that into this formula, then I see that this multiplication will become an addition. So we'll find that the observer 2015 entropy is equal to the entropy of the observer 2065 plus the logarithm of this factor. So what I get is essentially Kb times n times ln2. And this is this I can also write as the gas constant times the number of mole. So in other words, the entropy that this observer here assigns to the system is exactly larger by this amount that we saw before. So here, what this observer would say is H is equal, so let's just normalize. We can always define the entropy with an arbitrary constant. So we can just choose the constant so that this is 0 here. And in that case, this observer would say the entropy here, in this case, is 0 because here he knows the number of particles. So here, this additional thing goes away, whereas here, he has mixed them. So here we have uniform distribution over all the types. Actually, we still would know that there are equally many of this type as this type, but this doesn't matter asymptotically for large n. So in this case, the entropy would be Rn times ln2. Whereas for this observer here, he would say the entropy is 0. He only has the number of states, which I normalize to 0, and here it's also 0. So we see the entropy change from here to here is actually, so here we have exactly this delta that we saw before. So in other words, we have retrieved the result that we saw before. So before, in phenomenological thermodynamics, we have seen that there is an entropy change from here to here. The entropy increases by this amount, and there's no entropy change here. And so we have now seen exactly the same thing, even quantitatively the same thing, using the tools of statistical mechanics, which is based on a very different notion of entropy. But of course, these two, the reason why both are called entropy is that they somehow coincide in some way. And by the way, I will make this connection more precise tomorrow in the lecture. Why is it actually the case that with these very two different approaches to entropy, we find the same numerical results? Because a priori, this is even mathematically a very different object. This has something to do with probability distributions, whereas the entropy that we looked at yesterday in phenomenological thermodynamics is based on energy, on heat flow, and so on. So it's kind of maybe a priori surprising that one gets the same numbers. But it's not as much as a surprise if you understand later how these two things are connected. Anyway, what this shows is, again, what I explained before, and let me repeat that. This observer has more information initially, which he loses here, whereas this observer never had this information, so there is no change of entropy in this case. Yes?
I think where's temperature here is Kb and Rn.
Temperature?
Yeah, T. So delta S was nRT ln2.
Delta was n. Did I write nRT? Okay, maybe I should have. Okay, so this was then wrong. So what I should have written is delta S, in this case here, should have been NR ln2. If I put a T in addition, this was simply a mistake.
I don't know, maybe I just made a mistake.
No, it could be that I put a T, because if one would calculate the heat flow that is needed, then it would involve this additional T in order to. So if one, for example, asks oneself, what is the amount of heat that is dissipated if I go from here to here, then it has exactly this additional T, and it may have been that I just put this T. But this is wrong, so this should be the correct formula. Okay, so this now ends the kind of review and additional analysis of this example of yesterday. Are there any questions regarding that? Or maybe also questions to yesterday's lecture? Yes?
Is it possible to measure that heat that is lost in the near view version?
Aha, okay, this is a good point. So could one somehow now do an experiment where this quantity is relevant? And the answer is yes. However, I can only do that in an experiment which involves a mechanism for distinguishing the two particles. So what one could do is to do the process that I explained yesterday. So one could put these semi-permeable walls and then actually first separate the two gases and then would do that here. So you would actually use the semi-permeable walls, and then using them you could kind of compress the whole thing to one system. So what you could do, maybe I write that briefly, it's kind of similar to what I said yesterday, but just to summarize this. So you could essentially from here to here with semi-permeable walls achieve a situation where you have only half the volume. So if this thing here is V half the volume, then you really end up with half the volume, but you have both particles in the same, both types of particles in the same volume. So the way you would do that is you put the semi-permeable wall here. I mean, you remember this thing that I explained yesterday with these kind of nested boxes. So you move them into each other, and this can be done without any work. So there's no heat in this process. However, now to retrieve this situation here, you need to expand the whole thing. And during this expansion, you would see a heat flow, because the system would cool down when you expand. So it has to be compensate this by a heat flow into the system. So the answer is yes, there is an experiment which would give you exactly this amount times T as the work. However, this is an experiment which the old observer could never carry out because he couldn't do that step. So if one would show him this experiment, he would, of course, then be convinced that there is, yes, he would think this is magic. How could this, because from his perspective, it would look as if this guy just compresses the gas without any energy. It would look like magic to him. But he would, of course, then realize that there are processes which he wasn't aware of. So he would realize his theory was incomplete, but not wrong. That's still important. So he just didn't include that process. Yes. Okay. Are there other questions regarding that? Okay. If not, then I would just again remind you. So also this example showed, and please always keep that in mind because that's usually always implicit. Entropy also here is a property of the information or knowledge the observer has about the system. So it doesn't make sense in general to say the entropy of the system is this number. Of course, people usually say that, and they are not wrong, because what they mean is the entropy of the system from the point of view of kind of a standard observer. So if we do thermodynamics, we don't always mention the observer. But we have to keep in mind that there's always implicitly in all these statements an observer. So if we say that the entropy of a system is whatever, 1000 kb, this means that there is apparently an observer whose knowledge about the system has this quantity. And so also terms like an entropy source and things like that have to be understood in that way. And if you keep that in mind, so if you read about paradoxes, then it's exactly usually this thing that you have to keep in mind, and then the paradoxes resolves in a quite simple way, usually. And we will see that now. So I will now look at one of these famous paradoxes, which is related to Maxwell's demon. So you probably have heard about Maxwell's demon. Let me briefly just remind you of that. So Maxwell's demon is this experiment, Gedankenexperiment, suggested by Maxwell, where he said, let's imagine we have a box filled with particles, and again we have a wall here, but with a little hole in it, and here we put a kind of trapdoor. So this trapdoor has the property that if a particle comes from the left, it can be opened by the particle's velocity or by the particle's momentum, and the particle can pass through. However, if a particle comes from the right, it will not pass. Actually, there are different versions of this demon. There's also a version where one said, let's just have a door which lets fast particles pass. So only fast particles are strong enough to kind of open the door and keep the small ones on one side. So at the end you have those. But let me, for the moment, stick with this version. So only particles from the left can pass. So after a while, you will find a situation where only very few particles are left on the left, and most particles are on the right. So you have created a pressure difference, and once you have this pressure difference, you may use that to drive an ordinary engine. And so therefore going back to this situation, so here you extract work, and then you start again. I mean, extract work, you should do that ideally. For example, you could think of an isothermal process if you want. So you kind of let this gas here isothermally expand again against the cylinder that moves in this direction. And then the temperature and everything is the same because you did it isothermally, so you can run this process endlessly. And this would obviously now violate the second law. So to come back to our framework, if you would now say the set of states is described as the set of states that this gas can have, and the allowed processes includes a process like that. So so we would just say in this set A of allowed processes, there is this trapdoor process that brings us from here to here. Then this set A would, in this framework, not be allowed because it would violate the second law. And now we have exactly this situation that we have to ask ourselves, so maybe the second law is not physical, and there are physical situations which are correctly modeled by this set but violate the second law, or we did something wrong in the model, and this process from here to here is actually not possible. And I find this, this is a very old and famous example. Personally, this was one of my motivations even to study physics. I read about this example when I was kind of small in primary school, and I found that really fascinating. And I always thought, people are stupid, why don't they build that? It seems so easy, you just put this trapdoor here. And I even saw an experiment where people did it with billiard balls. So they had a table which was shaking, simulating the movement of the atoms, and these were little billiard balls, and there was a trapdoor in the middle, and indeed, of course it worked. So all the billiard balls ended up here. And so I asked myself, why don't people just build that on the level of atoms? And I asked people I knew at that time, probably they were not physicists, but I never got a convincing answer. So I had to study physics at the end, to find the end. So now, unfortunately, I no longer think people are stupid because they're not building it. So I now see a reason why they cannot build it. But let's now consider this a little bit more deeply. So why is this impossible? And to explain that, I think it's a nice way to explain why it's impossible is actually to look at first a much simplified scenario. And this was suggested by Szilard. Maybe I just replace it now. So instead of Maxwell's demon, we now look at Szilard's engine. It's essentially the same principle, but it's a little bit easier to analyze because it's much clearer what this mechanism is. Here it's not so clear what this trapdoor, how this exactly works in practice. And Szilard engine was much more concrete. So what he said is, let's also consider such a box, but let's, for simplicity, just assume there's only one particle. By the way, everything that you have here also works for more than one particle. It's just more difficult to draw, and you would have to wait longer. And so in principle, the number of particles can be arbitrary. However, it's best understood with one particle, and this was also the suggestion of Szilard to consider one single particle. So his setting involves essentially this box, and we also assume that this box is somehow in contact to a thermal reservoir which is at temperature T. And Szilard assumes that this one particle gas is an ideal gas. So he essentially applies the equations that he has for an ideal gas. One may, of course, say that this is problematic for a one-particle gas. However, as I said, everything I said also works for more than one particle. So one can go to this limits where there's more than one. One has to just be more careful. So whenever I put the wall in the middle, I would have to put many walls and stuff like that, so it would be more complicated. But the reason why there is a problem is not hidden in fluctuations that you have because it's only one particle. So that's not the problem. Okay, so this is an ideal gas. And what he also assumes, so that his assumption is that this is again about, let's say, if you think formally about the set of allowed processes, that we can insert or remove walls at no energy cost. And here again, this is hard to justify that it's exactly zero, but the energy cost can be made arbitrarily small. So this is clear again for a larger gas that inserting a wall into a huge cylinder of gas requires much less energy than or the energy required for that is very small compared to the inner energy of the gas and so on. So we assume that, and we can also use pistons to extract work. So we can use the pressure of this gas and, for example, use that to lift the weight, which would then store the work that we get from the system. So Szilard was now proposing an explicit mechanism to extract work. So Szilard's process is kind of a sequence of steps. So he starts with this box, and I will not draw the thermal reservoir always. Just assume it's always there. I'm just not drawing it for simplicity. So we have this particle here. And now in the first step is very simple. He just inserts a wall in the middle. So we have this situation now. Now the second step is insert the piston. So this would now, of course, it sounds now I could have done that already in the first step, but it's useful to separate this. So we kind of think of a piston here, and this piston is inserted until it reaches the middle. And then we remove the wall. Also, or maybe I do, yeah, let's do that. We remove the wall. So when we remove the wall, let me do it here because it's actually a cyclic process. Let me draw it cyclically. So the piston is now here, but the wall is no longer there. So the gas, the one particle gas now presses against the piston. Now we extract work by this process I said here. So we can use the piston to extract work. So what this looks maybe as a picture as follows. So the piston is now pushed towards the left by this particle, but with some force. So we could, so sometimes people draw pictures like this. So this piston could have, could be connected somehow to a mechanism here. So here this is a little wheel, and here is a weight. And you see, if the piston is pushed out, this weight is, so as the piston moves in this direction, the weight goes up. So this is kind of how you could imagine extracting work. And now we can again remove the piston. And we are back in the original situation. So this is a cyclic process on the system itself, where we kind of extract work. And this is, by the way, I mean, because we have the thermal reservoir, this is an isothermal expansion. So the energy we extract here comes from the reservoir. So it's not that the energy conservation is violated. It's just that what is violated is, again, the second law, because energy from the heat reservoir is transformed into work in a cyclic process. Now, again, we have the choice. Either the second law is wrong, or we have now used a process or assumed that there is a process which actually doesn't exist in nature. We have these two options. Now, as you may guess, I mean, we don't have such engines in practice, and the second thing is the case. So there is something we cannot do here. So maybe some of you have seen these examples, maybe some not. Do you have a question?
Is there a mechanism in this process whereby we know on which side of the wall the particle is? Because or does it not matter?
No, this is an important point. So, indeed, so the question is, how can we know, and now drew the particle on the left, so how can we know it's on the left? And this is indeed important. So I will just have to modify the mechanism a little bit. So, of course, the particle could also be on the right. And if it's on the right, I would, again, insert the wall in the same way, but I would have to insert the piston on the other side. And so at some point, I should measure on which side the particle is. So this is indeed something I need to do in order to make this process. And this is actually an important thing I need to include in my description. So it also answers actually my question, what is the problem with this process? So your question was actually an answer in some way. So, but let me briefly just remind you that this step here, inserting a wall, by assumption doesn't cost any energy. Inserting the piston here also doesn't cost energy if I know where the particle is, because I'm inserting it on the side where I have a vacuum. And here this, of course, extracts work. And here removing the piston again should also not cost any energy, because it's like removing a wall. I mean, I could first put the wall here and stuff like that. So, but indeed, there is a problem, because here I need to know from which side I want to insert the piston. And each time I run the process, the particle may be on a different side. So I need to get that information. And indeed, people for a very long time thought that the measurement here, so I need to carry out the measurement. Everyone agreed with that. And they would have argued that measuring on which side this particle is would cost exactly or at least as much energy as I could extract in this process here. And people had different arguments. There are actually zillions of papers you find in written even in the 40s, 50s, 60s about these measurement processes. For example, people argued that in order to detect the particle, you need a photon, at least one, that kind of hits this particle, and to generate and the photon needs to have a wavelength which is kind of high enough to detect the particle. And then they argued that generating this photon would cost a certain energy and so on. However, later Charles Bennett, who is also known in quantum information for his contributions to quantum information theory, in particular quantum cryptography, he also analyzed this problem, and he found and proposed an explicit mechanism for measuring the particle position that doesn't consume any energy. So he showed that there exists. A measurement with no work cost. Or, I mean, it goes to zero. You have to do it very slowly, and in this limit where you do it very slowly, it doesn't cost any energy. So he argued that this is the case. And indeed, from today's perspective, it's kind of relatively easy to see that such a measurement that costs no energy must exist, because the reasoning is, by the way, as follows. So instead of thinking of a particle with a gas, you could also say this is essentially a qubit, because you just could say I mean, if you build an ion trap or so, you could say the position of the ion is seen as the kind of position or as the value of the qubit. And so people build, in that sense, people build such things. And of course, one can measure, so measuring the position of an ion, whether it's here or here, is actually in some way nothing else than a controlled knot operation, where the knot, so you could see, maybe I should say that here. So measuring, so if I have here a system S that I want to measure, and here I have a reference system that I put into 0, then I could draw this circuit here. And if, so this system could be in two states. Let's say it's either 0 or 1, left or right. Then, of course, the system isn't changed. But here I have the measurement outcome. So this is 0 if S was 0 and 1 if S is equal to 1. And of course, you could say this is not really a measurement, but this would be sufficient. So you have extracted the information from the system, and you could now use that information to, for example, decide whether or not, or from which side you insert the piston. And the controlled knot operation is a reversible operation. It's a unitary, and it's kind of widely accepted that in principle, unitaries can be carried out without an energy cost. Of course, in practice, that's again very difficult. But essentially what Bennett's argument from today's perspective is to say, oh, this measurement process that I need to do is just a Z-knot operation, and the Z-knot operation is reversible and therefore can be carried out at no energy cost. Anyway, I think today it's widely accepted that this is, at least in principle, a correct argument. There is no, I mean, even though it's in practice very difficult, there's no physical reason why this process that Bennett suggested shouldn't be possible. So we can measure here. And so here I should say, instead of insert piston, I should say measure and insert piston. Okay, now we are back with a problem, because now we have measured it, so we can. So your concern is now addressed. And I even argued that the measurement can be done without energy cost. So where does the problem lie now? Does anyone see that? What could be the problem? Yes?
I suppose that the reservoir comes back in exactly the same state.
Aha, this is not, okay, that's a good point. So you're saying the reservoir, it's not cyclic maybe because the reservoir is not back in its original state. So this is actually not required. So the second law would just say there is no way you can extract heat from a system without changing anything else. So what you are allowed to do, of course, is to extract heat. So indeed, the reservoir would be in a different state. It would have spent some heat, so it would have lost some energy, but that's fine. That's still a violation of the second law. So that's not the problem. So if the process worked, it would really in some way leave the reservoir in a state which is kind of not a problem concerning the second law, because we have only extracted heat and not done anything else to the reservoir. But there is another problem, which is
it the energy cost of the walls?
Not really. So maybe you should now remind yourself of what I told you yesterday or today about changing perspectives and things like that. Or that the entropy, the description of the system is depending on the information we have about the system. Yes?
We include information in the first step, but before we just have one state, and then after the first step we have two states?
Yes, I'm not sure I completely understand what you meant. So you're saying we have two states. I mean, in some way we got the information here about the system. Is that what you're saying?
No, before that.
Yes.
At first we just have one box,
Mm-hmm.
and then we have two boxes. So
Two boxes. Aha. Yes. Okay. You're worried that here we have different information here and here, but you could say this wall here is just kind of a mental thing, because I could even here ask myself, is the particle left or right? So the number of states of the system, I mean that the particle can be on the left or on the right, was already here the case. So I would say inserting this wall doesn't really change the information as long as we don't look where the particle is. But you have add something?
Yeah, is Bennett's law universally applicable to all systems? Because you now showed us a system where in a standard qubit you can make such a worthless measurement.
Mm-hmm.
The question is it true for this system?
Yes, it is. So, so the question is, I said now, okay, some system can be measured with the C node. So this was just an explanation, but actually Bennett gave even an explicit mechanism for that particular system. But in some way, what I wanted to say with that is that even if we think of more realistic implementations, which would be ones that would use today's quantum technology, where we would actually not want to do a gas, but do something on qubits. And we will look at such systems tomorrow. Bennett's argument would translate to that. But it's quite interesting. He gave kind of a mechanism. It's really a mechanism with mechanical elements that would actually extract this information. But logically, the mechanism also corresponds to such a thing. Yes, there are now many suggestions.
Well, there's one thing is that certainly the one creates two systems, and the arguments based on the different observers assumes that certainly one creates two more or less identical systems. And that's not the case because there's no particles in one system and there's one in the other. So the energy is different.
So you're worried about the fact, if I understand correctly, that once I insert the wall, I generate an asymmetry. One particle, one system has now a particle and the other was not. Yes. It's correct that I generate this asymmetry, but I'm not using this asymmetry here. So I'm not using symmetry, so I actually want to generate this asymmetry. So in some way, it's fine to say that now I have one system with a particle and one without, and I use them in a different way. I say, let's insert the piston into the one without. So generating the asymmetry by itself is not a problem. You have also.
Because when you made this measurement and you made this information, you have to store this information somewhere. So I thought that if we go in a circle, the time should be set.
Yes, so you're.
Memory, okay. Maybe this is setting to the memory when some into energy to do that.
Yes, so this is an interesting remark. So you're saying if we measure, we need to store the information of the measurement outcome. That's correct. So we need to do that, and we need to take care of that. So let me come back to that. That will lead us to the right solution. But let me nevertheless, we'll take the other.
As I see it, we have two processes here. One is inserting a wall, and the other is inserting a piston. So if I go from 1 to 2, I can get the same state by not inserting a wall, but the piston at the right-hand side and then pushing it in. So inserting work into the system. I can get the same process. However, with different work done, and this violates this first law.
Oh, this is an interesting remark. So you're saying there would be a different process to go from here to here, namely just inserting the piston slowly, and this would violate this statement that we had yesterday. Okay, so it wouldn't, I would argue, because if you insert, so your process that you're suggesting is to compress the gas from here with a piston. However, if you compress the gas, you would either have to choose whether you do it isothermally or not. So of course, in this process, this would be isothermal. So compressing the gas would correspond to an isothermal compression, which would dissipate heat to the reservoir. So in other words, it's not an adiabatic process. And because this first law that we formulated would only hold for adiabatic processes, so only for processes that we can do on the system itself without the help of the reservoir. Because this process is not possible like that, it wouldn't count in this first law. So in other words, the first law, so this process that I describe here is completely adiabatic. You don't need the reservoir in the description. Whereas the process you suggest would need the reservoir unless the temperature is increased, and then I wouldn't reach the same state. Okay, I don't know. Yes?
Are we assuming that this is a cycle?
Yes.
Well, then if we, so like, if we go back to 1, we're in the same state as where we left off.
Aha. Yes, so the same state in the sense of thermodynamics, not the same microscopic state. So we assume it's not necessarily in the same position as before.
Yeah, but does it have the same energy, the particle inside?
Yes, it should have the same energy. And this is guaranteed because this is actually the case because I assume there is this thermal bath always here. So it will always thermalize. So of course it will lose energy here by expanding, but this will be compensated by heat flow from the reservoir to the particle. Yes?
Does it have to do with the feedback that we need to do from the information we extract?
The feedback we need to do.
I mean, you can do this measurement that you extract some information without energy cost, but you need to use this information into your system, no?
Aha, yes, I need to somehow use the information to insert the piston, but once I have the information, this is again an assumption that I can insert pistons without energy, and this is indeed the case. So actually, again, Bennett showed that inserting a piston into a vacuum, once I know on which side, can be done without energy. Okay, let me now take a last suggestion. I think you had one, and then I maybe continue with my solution.
So in your first description of the particle, you need to take the full state space of your whole solid, and then once you did the measurement, you have more information. So
yes, here when I do the measurement, I have more information, yes.
Your description needs a smaller state space, and this would also change your description of entropy.
Yes, yes, right, yes. So this what you're saying is now really referring to what I said before, and this is indeed the problem here in the first place. I mean, we have now heard many answers, and some of them come very close to what I'm going to tell you now as a solution, particularly yours and yours. So let me just continue on with what you said. So let me formulate it in my words. I'm not sure it will still coincide with what you said, but so we are measuring here the system. So when we gain information about the system, then we are kind of now, if you think of, again, these two observers we had, the old one in 1865 and the modern one. Of course, if we tell the old one, actually, there are two types of particles, and one type is here and the other one is here, then he's now as if he was the modern observer. So he gained information, so we gave him information, and therefore the description he had and used before is no longer applicable. And the same happens here, although the amount of information is very small, but of course we have a small system, so it's actually relevant compared to the system. So here we suddenly are kind of talking about, here we are talking about implicitly about an observer who doesn't know where the particle is. And here, after the measurement, we are suddenly kind of talking about an observer who knows where the particle is. So we have observers with different knowledge about the system. And this is exactly like in the scenario before with the 1865 and 2015. These are, you could say it's the same person with different knowledge. Doesn't matter that it's actually a different person. So here it's maybe the same person, but he has now very different knowledge about the system. And so these two views we are not allowed to analyze a process with two different types of information we have about the system. So this now seems a little bit problematic because that tells us we cannot do thermodynamics when we measure a system. However, we can do it, and this now refers to what you said. Of course, we can still, the only trick we have to do is to say, let's model the information we get also as part of the system. So in some way, there are two different points of view you could have. You could say, here we have the observer, and here we have the system. And now, if we do a measurement, we get some information. Let's call that information X that we get about the system. So measurement with outcome X on the system. And now we could either say, now this measurement outcome is kind of now known to the observer. And now we have kind of, this is now like a different observer, observer prime. This is kind of what it now is. This would be one view. The other view would be to say, no, it's the same observer as before. So the observer is just a person who describes the system. But the observer doesn't even need to know the outcome. We could just say it's sufficient if the outcome exists and is kind of, because the outcome is just needed to drive the mechanism here. So for our analysis, we can just assume the observer stays the same, but there is now somewhere as part of an extended system. So we could say there's an extended system, and here this is a storage which is first empty, and then when we measure here, the storage, so this is measurement, the storage is filled with the measurement outcome. So these are two different views. In this view, I really change kind of, so in this, I mean, it's of course the same process, but described in two different ways. Here I'm saying we have now an observer with updated information and the system remains the same. And here I'm saying the system is a system that includes a memory of the measurement outcome, and the observer just analyzes that from outside. So the observer is someone who stands outside and doesn't really look at the outcome. He would just say, the system was measured and the result was stored somewhere. And now you can imagine for thermodynamics purposes, this is kind of a much more or much cleaner description, because here we don't change anything on the observer side. We are just doing something on the system. We have now a larger system, but the observer stays the same. So if you take this point of view, we are not running into problems. Whereas if you take this point of view, we could say this is the same as, this is the old observer, 1865, this is a 2015, because he has now more information. And I told you, that was the main message of yesterday and before, we are not allowed to mix the two. So we cannot do an analysis that mixes these observers. So in order to apply thermodynamics in a clean way, we have to do it in that way. So we have to model the memory explicitly. Now you could argue that when we do standard thermodynamics with large systems, we are actually very much used to measure stuff. We measure the temperature and then do an analysis based on that measurement. This is not problematic, but the only reason why it's not problematic is that the systems are very large, and the amount of information we get by measuring macroscopic observables is just negligible compared to the entropy that the system has in total, because the system has so many degrees of freedom. So normally, it's just irrelevant. So it's actually still wrong, so we shouldn't do that. So whenever we measure something about the system, we are not allowed to update kind of the observer, because he has now more information. But as long as this information is negligible compared to the size of the system, we will still get the right results. However, here, and this is the only difference, I mean, this system is not special, it's just very small. So when we do a measurement on the system, the amount of information we get is comparable to the information that is needed to describe the whole microscopic state of the system. And therefore, we cannot neglect that problem that we have now updated the observer's information. So the bottom line of this is what you said before. We have to just include in our description a record of the measurement outcome. So I could just adapt my process, and maybe I do that with an additional color. I say here is a memory, and this memory is always there. First it's empty, and then here it's still empty, but now I measure, or I measure, and then it tells me, the outcome is X. Or maybe actually it's cleaner to have an additional measurement step in between. So I could say after the measurement it's now X, and now the memory is in X, X, X. And now you said something interesting, namely you said if we have this memory thing, then of course we need to restore it, because otherwise it's not a cyclic process. I mean, here the memory was empty, and here it has this thing. So in order to go from here to here, we have to erase the memory. And there's one thing I should add here to make that clear, which I forgot to say before. So what Bennett said, that the measurement is possible without energy cost, this is only true under the assumption that you have an empty memory in which you can write in your measurement outcome. So I couldn't just say, I anyway do a new measurement, so let's just not care about the fact that there is already an X inside. So this mechanism that he described only works if the memory is in a well-defined initial state. So in order to do that measurement without work cost, I need to make sure this memory is in is in somehow a well-defined state. I could also say the well-defined state is just that the particle is on the left or so, but this symbol just means it's some initial state of the memory, and I need to go back from here to here. So now I have introduced an additional step which was necessary. And now there's, of course, the question, can this step from here to here be carried out without an energy cost? And this is now exactly what, let's say, what today's understanding of Szilard's engine is, that it's this step that compensates for the work gain. So in other words, what one would say today in the analysis is that however clever you are, however clever mechanism you design to erase the memory, it will actually cost as much work as you gain. So how much work do we, by the way, gain here? This is something I should maybe say at some point. This is an expansion of a gas to twice the volume. And the simple calculation that you will do in the exercises means that tells us that the work we get is just the Boltzmann constant times the temperature of the reservoir times ln2. So this is the amount of work we gain in the extraction. And the claim is now that erasing the memory has to compensate that, because that's the only process where we are not sure that it can be done without energy cost. So it has to be that process that will cost that much work. And indeed, there are now many arguments that say that this is the case. And today, let's say the statement is maybe as follows. One could say that, or maybe I should first mention that the person who proposed that first was Landauer, and Bennett later made this more precise. But Landauer's statement, or postulate in some way, is the following. So Landauer's postulate says that any process that erases one bit of memory, and erase means to set it back to an initial state. So it doesn't mean to randomize it. It means, has this meaning, to set it back to an initial state, costs at least this amount of work, WKBT ln2. So this is how much you have to invest. That's what he proposed. And if we accept this postulate, then we have resolved the paradox, because now it's no longer a machine that extracts work, because in this step we will pay for everything to set the memory back. Now I should maybe say this T here is actually the T of the memory. So the memory is itself a system, and it has a certain temperature, and so the T is the thing of the memory. KB is some very small value. I think it's roughly 1.3 times 10 to the minus 23 joule per Kelvin. But still, it's a positive value. And so this is now widely accepted as a fundamental limit. And one can make the following mathematical statement. One could say that if the second law is correct, then this postulate also has to hold. So in other words, this postulate is in some way a necessary consequence of the second law of thermodynamics. Or in other words, if you can really find a mechanism that can erase a memory at less work cost than that, then you have automatically broken the second law. So that's why it would be interesting. So in other words, it means it's very hard if you ever try to build a process that erases a memory at this work cost.
Maybe you're about to come back to this point because you made a point that this is the temperature of the memory.
Mm-hmm.
So, and you of course already have a reservoir with the temperature, which is the reservoir for the gas.
Right.
cylinder.
Yes. Mm-hmm.
So I presume if you take those two temperatures to be different, then you have the usual story of heat engines and refrigerators,
exactly.
and that Landauer's postulate corresponds to, or the numerical value in his postulate corresponds to Carnot.
Yes, exactly. Yes, that's exactly the case. So indeed, maybe I should. So here we have a temperature, which is the temperature at which I drive the Szilard engine, and then I have another in principle, I could choose the temperature of the memory to be a different one. So the memory itself is a system that could be connected to something with a different temperature, T prime, and to a heat reservoir with different temperature, T prime. And now, indeed, what I would need here is the amount to erase would just correspond on the T prime. So if the T prime was lower than T, I would need less work to erase the memory. So that sounds like as if I would gain energy, but what I've now effectively done is to transfer heat from this temperature reservoir, from the hot one, to the cold one that belongs to the memory. And this is what I could anyway have done with a Carnot engine. So this would no longer violate the second law. I essentially would have used the temperature difference between two reservoirs. So this would be a very kind of funny version of a Carnot engine that would work via erasure and creation of information. And if you make the calculation, you find it has exactly the Carnot efficiency. If this was all at the limit, of course, it's not so clear that you can really build it at this cost. Okay, so that's now was an example that should illustrate again how important it is to take care of the right use on the observer, and that if one does it in the right way, then the paradoxes resolve. But just so this thing forced us essentially to introduce a memory explicitly, and once we do that, everything becomes again consistent. The paradox just arose because we didn't make the memory explicit and included the information into the information the observer has, and this effectively corresponds to analyzing the system with two different observers with two different amounts of information. And this is, as I said, not allowed. Maybe I should say, because I mentioned yesterday that the heat production of computation is a very important thing, and this, by the way, gives us a bound on how efficient we can make at least classical computation. Or, I mean, it's kind of funny to, maybe I should do that briefly if there's a few minutes left, just to actually look what this number means. And if you, for example, look at, I mean, you can now look at different things you could erase. You can ask how much work does it cost to erase the memory content of this iPhone, but it's maybe more interesting to ask what is the memory consumption, what is the work required to erase the content, for example, of our brains, let's say. And I made this calculation this morning because it's kind of funny to see how much is there. So I'm not an expert in neurology, but I found the information quite consistently that apparently the storage capacity or the amount of information stored in the brain is of the order of, I think, 1 petabyte. So the storage is roughly 1 petabyte. So this means these are 8 times 10 to the 15 bits. And so if you now look at the whole thing at room temp, or let's say, let's take the body temperature, or temperature 300 Kelvin to make the calculation easy, then we can just insert these things now into the formula. So we just have to look at this value. So this value is now 300 times ln2 times the Boltzmann constant, which I wrote down here. So I have to multiply all these numbers together. And so this gives me roughly so here I get 2,400 times 10 to the 15 times 10 to the minus 23. So, yes, and I hope, okay, yeah. Okay, let's forget about the ln2, just as an order of magnitude, because some people also say it's a little bit larger. So the estimate is between 1 and 2.5 petabytes. I have no idea how this is determined, but so the order of magnitude we get, so this is roughly 10 to the 18, so it's something of the order of 10 to the minus 6 to 10 to the minus 5 joule. So this is kind of the energy that would be required. So this is at least a noticeable, it's a very small amount. It corresponds maybe to lifting 1 gram by 1 a few millimeters or 1 millimeter. But at least it's noticeable. It's no longer completely negligible. But
one way to measure it would be the energy flows in and out of the brain, or in as work, usable energy, chemical energy is about 10 watts.
Okay.
So this would be about 100 nanoseconds worth of metabolism.
Yes,
So
exactly.
From that point of view, it's pretty small.
It's very small, yes. So one can now ask how close is the actual process in the brain to this theoretical limit, because this is just a limit. So this just tells us physics will never allow us to do it below that amount. And of course, in practice, information is stored not in an optimal way from a thermodynamic point of view. And one could now actually probably try to see or do such an estimate to see how close it is. Of course, the brain will not constantly raise itself, so it's be hard to do, but you could do it with a computer. And actually, if you do the calculation with a computer, then you get numbers which are kind of surprisingly large. So I also did the calculation this morning for for a supercomputer. So the fastest so if you take supercomputing, then you have something of the order of 30 petaflops. And if you now make some assumptions about how many bits each floating point operation involves and so on, you find roughly that this corresponds to 1 watt at room temperature. So even if you would build your computer in an optimal way, but you still assume that, so you would just run a trivial program on the computer that just erases and outputs zeros. So the computer would essentially get as an input a random number and has to output zeros. It's a very simple calculation for a supercomputer, but even if you do it in an optimal way, the computer would consume 1 watt. So now, of course, in practice, the supercomputer will consume much more, but not so much more. So the kind of the fraction between this and what it actually consumes tells us how far we are away from Landauer's limit. Yes?
Just maybe, I don't know if it's a question or comment. I guess it's not even good to reach Landauer's limit, because I guess the time you need to do the operations kind of goes to.
Aha. Yes, that's it. So the question is now, what should we do? So if you ask a computer engineer, should he try to reach Landauer's limit? I would say, and you are arguing that all these processes are probably only feasible at this efficiency if you do them arbitrarily slow, which is probably the case. However, there is one important thing one could say, namely, there is this whole domain of reversible computation. So if you want to do a computation, it doesn't mean that you need to erase bits. And I don't know whether there was already a lecture about computation, but in the field of quantum computation, we do actually all the computations in a reversible way. All the gates, at least in the gate model, the gates are usually reversible. So Landauer's principle only applies directly in that form as I've written it to the erasure process, or more generally to irreversible gates. However, it doesn't apply to reversible computations. So in principle, if we take a circuit that we would use for example, draw for a quantum computer, but we could, of course, even do a classical computation on that, and do it in this reversible way as it's usually done, then the only thing that would contribute to that is at the end of the day, when we did the calculation, we have the result and some other registers which we don't use any longer. So we would only have to erase them. So I think the key to go to larger computing, to overstep this, is actually to build reversible computers. And this is something people are already thinking about now in the supercomputing scene. I mean, of course, this is relevant once we are that, but we are already only a few, 2 or 3 orders of magnitude above that with the most efficient silicon chips. Yes?
How do we define the process of erasing? Because if I have 100 bits,
yes,
I can just say that instead of explicitly performing some erasing operation, if I want to use them again I'll just forget what's in them. I won't
Yes.
do any operation. I'll just overwrite them the next
Yes.
time I. So how are you defining an
So
array?
the eraser is defined as the operation that takes either a 0 or 1 and certainly outputs a 0. So indeed you could say that this is not what you want, but so you could say it's okay for you if we just keep that. But this is not, so maybe I should, in the last 2 minutes, say there is a more general version of Landauer's principle. And the more general version tells us the following. So if you have, so this is actually a result, a relatively recent research result that, and this is actually research that we also did in our group, which is the following. So the generalized Landauer principle tells us that the amount of work that is needed is at least kBT ln2, but there is now an entropy here, and the entropy is the entropy of x given y. So what is x and y? So if I look at a process with an input x, and I have some arbitrary computation, this could be an eraser, or it could just be a gate, or it could be the whole brain. You could take whatever you like, and you have some output y. Then what this generalized principle tells us is that the amount of information that we are essentially, or that is relevant for the principle, is kind of the information we have about the input given the output. So one particular case is if this is a reversible computation. This again relates to what we have heard before. So if this is a reversible computation, then by definition, so this means the entropy, the uncertainty about x given y. So if it's reversible, in principle, there is no uncertainty about the input if I know the output. So in that case, the Landauer principle gives only the trivial bound 0. However, if I do, for example, an AND gate, which is something I clearly want to do, so I have here 2 inputs, x1, x2, and I have an output y, which should be the logical AND. Then clearly from the output, if it's, for example, 0, I cannot determine the input. So I have some positive entropy, and this will contribute to that. Now, you could say that, so now there is, of course, a reversible version of the AND gate that I could do. Or there's, for example, the Toffoli gate. But the Toffoli gate, if I want to execute a Toffoli gate and generate an AND operation, I would need to feed into the Toffoli gate some zeros. And this is exactly why I sometimes want to have erasure, because I don't want to feed in something unknown. So I need to feed in 0. So erasing really and putting it to 0 is important for the future processes usually. At some point I will always lose the information. So at the end you can look at the total computation and then ask this question. And now, of course, if you do it in a more, so at the end what is relevant is this thing for the individual steps. For the whole computation, this will just give you a bound. And so the long answer to your question is now, it depends on your application. So eraser means putting it back to 0. This is, for example, needed for Bennett's measurement operation, as I said. I mean, he needs that it's 0. But if it doesn't mean, let's say, if you don't care what the other outputs are, then it's fine. And indeed, this is maybe an interesting consideration. So this Szilard engine that I described before actually works and can be done if you live with the fact that you would just fill up memory. So instead of saying, let's erase the memory each time, we could say, let's just give the mechanism a new memory. So we had this cycle of the Szilard engine, and I said, here we restore, or here we erase the memory. But of course, instead of erasing the memory, I could take out the memory and provide a new bit which is in a 0 state. And then the mechanism actually works. I just pile up random bits. So if I, for example, do the mechanism, I take this smartphone here with an empty memory and run the Szilard engine each time with a new memory bit, then in each cycle it will fill one memory bit with a random bit. And after n cycles I have n random bits, but the cycle actually works. So I have actually, in that case, transformed heat into work. The only price I pay was that I filled up an empty memory with random content. And of course, if I erase that again, I would again compensate that. So I could somehow use an empty memory to build an engine. And this was actually a proposal by Bennett, and I would like to end with that. He had this idea to drive cars with empty memory. So you would essentially take your empty memory stick, put it into your car, and then you can drive to location B, and then the memory stick is filled with random bits, but you're there, and you have just transformed. So that works in principle. You just need a lot of memory. You saw before, I mean, the petabyte, so this, even the human brain wouldn't bring you very far with your car, but maybe I should build more efficient memories. Okay, so that, or maybe I should first take the question.
Today, randomness is also valuable, right? So you could invent, you could sell your memory for good money because it's full of random numbers.
Oh, yeah, that's a good point. Yes, I could even sell my memory at the end as a random number generator, yes. Yes, we will hear actually this afternoon about randomness, and randomness is an important resource in some way. But from a thermodynamics point of view, randomness is actually waste. But indeed, in cryptography, good randomness is, on the other hand, something you pay a price for. So maybe you should combine these two things. Yes?
Are there any estimates as to how efficient the human brain is in terms of computation? I know you can't.
I'm sure they are, but I don't know them. But maybe I should look up and see. I just know the values for chips, for computer chips, and there it depends. So the commercial ones are 3 or 4 orders of magnitude, so 1,000 or 10,000 above this limit. But in the lab, there are constructions which are very close, just 1 order of magnitude, like a factor of 10 above this limit. Yes?
What if I don't erase the memory every time I know that it's 0? Because it's erased by default.
You know that?
Well, every time I know that I have a 0.
Ah, this is an interesting remark. So the question is, if I already know it's a 0, why should I, then I don't need to erase it, so I could save a bit. But this is a circular argument, because in order to know that you have a 0, you would need another memory in which this knowledge is stored. So, and then you need to again erase that memory. So indeed, if you know what the value of the memory is, then you can erase it at no work cost, even if it was a 1. Because if you know it's a 1, what you do is you just flip the bit. And flipping a bit is a reversible process. So it's only hard to erase a memory whose content you don't know. But if you know the content, you can do it at no work cost. The problem is just in order to know the content, you need another memory, and then you're done. Yes?
Can we say that change the long term process to write?
Sorry, I didn't
change the word from erase to write. What bit of memory?
To write 1 bit of memory. The question is what you mean by write. I mean, if you mean write a fixed value, then it's the same as erasure. If you mean write a random value, then it's exactly the opposite of erasure.
Opposite of the creation.
Yeah, because essentially erasing takes a random value and makes a fixed value out of it. And the opposite is kind of take a fixed value, take a memory in state 0 and make a random value out of it. And I mean, it really depends on what you mean by write. Write could mean write a random value or write a fixed value. Yes? Yes, I should also answer Maxwell's demon. So Maxwell's demon, or Maxwell's paradox, has exactly the same explanation. So in some way, the trapdoor serves as the memory. So once the trapdoor is hit by a particle from the left, the trapdoor will open, but now the trapdoor, the mechanism, somehow remembers that the particle was there, because it will now swing, or it has some energy. So you have to put it back. So you could interpret the state of the trapdoor itself as a memory. So by looking at the trapdoor, you know, there was just a particle passing, or there was none. And now what this all implies is that in order to reset the trapdoor into the closed state, this is like erasing a memory. And you would exactly, again, use this KBLN2 of work, which would exactly compensate, again, what you gain by the Maxwell demon. Okay, so with that, I think I can this time end on time. So thanks for your attention, and then we will continue with the last lecture tomorrow, which will be more quantum then.